mà bạn ấy gửi ấy.
Ok, cảm ơn thầy nhiều.
All right. Yeah. Thank you. Thank you, T. So everyone can try getting the files in your environment, and then we can get started. Let's start with, let's see, which one should we get started with? Now let's get started with PA underscore lab underscore 25. We can start with that first. All right, let me know if you want me to slow down on this lab, but you guys can also try out this lab. I have opened up this lab, PA underscore lab underscore 25. We can get started with this, and then we'll check from the make file first. So everything we check from a make file so that we can get familiarized with the options that we need to bring up power verification. So the easiest one is to make all, which is a post-sim mode. We can run the simulation and then we'll bring up the debugger. So make all, we have clean option, clean run, and then there's a compile. So compile is a usual compile. We just use vlog, and then all of our system verilog file to compile it together. And then we have our optimize phase. So optimize phase, we use vopt, our top design unit, top instance, and then output our optimized design unit. And then we have dash debug so that we can debug it together. Then minus design file and then your specific design file name. Then at VOP stage, we need to include also our UPF. So UPF is included here, dash PA underscore UPF. And then U1 UPF is our UPF. Then we can also choose to specify what version of UPF we are using. If we don't specify it, that's okay as well. And then here we specify which PA top is the instance of PA top. So D1 is our instance top at PA. So we also have additional options on PA. So we switch on check equals to S. So static checks is switch on. And then we also have generated report and gen report of source and sink information. Then at the sim side, we have regular vsim, and then we are doing this in batch mode. Our optimized DU name dash PA is necessary if you want to do power verification. And then to log our waveform dash QFDB equals to signal plus M. sg, and then I will do command run all and then quit. So you guys can try running make all, and then let me know if you got any results from make all. Yeah, sorry, T. There's one more file that I didn't manage to send to you. It's a PDF version of the lab guide. Maybe I might have to trouble you to help send out again the one PDF file. So that PDF file is for PA underscore lab underscore 24. So, okay, I hope everyone managed to run it in your environment. Let's see. See if I...
Mời mọi người tải giúp em cái PDF mà bạn gửi vừa nãy nhé. Vẫn ở trong cái link vừa nãy cả đấy ạ. Ok, thank you Goanh. I send data and PDF file for everyone.
Yep, thank you, thank you.
Thì có phải là file mà ta.gz phải không Thi? Cái file đuôi á. Alo Thi ơi.
Cái file dữ liệu á? Hay là
Đúng rồi, cái file mà file PDF là bạn gửi là cái
file là lab
file...
training ấy. File lab sheet training ấy, chỉ có một file PDF thôi.
Ủa thế hả? Rồi cảm ơn
Vâng.
em.
Có một file PDF thôi nhé, là lab training. Còn mà dữ liệu nào dùng lab mà ship-25 ấy nhé.
Ok em, rồi.
Thấy chưa?
À,
Ok,
anh thấy
được chưa anh Việt?
anh thấy là có một file BA Lab 24 với lại BA Lab 25 đúng không?
Vâng, đúng rồi.
Rồi ok em.
Với một file PDF có chưa?
Rồi để em tìm rồi em tìm lại kỹ lại. Rồi cảm ơn em nghe.
Ok. Goy, you can start.
Okay, yep, sure. Yep, so I'll continue here. So if we go into the first lab, which is PA underscore lab underscore 25, and then I make all. So doing make all, let me bring this bigger. Doing make all, it actually gives us an error from this lab test case, but we don't have to worry about this error because this error is intended. So if you guys hit this error as well, then you can try to resolve the error yourself, but I'll also demonstrate the error here from my side so that you can have a watch. How do I resolve this power verification debugging this error? So if we get this error, we don't have to worry. We just have to remember where to get the log file. So the log file is actually deposited in the power aware report. So if you can see in our run directory, because we run the option vopt with pa-gen report, we have these power aware reports here. So let's see what's inside these power aware reports. So in Power Aware reports, the one that we want to see is one of it is message vop.log and also report p8.txt. These are the two general reports that we should see so that we can identify what's wrong with the design and then we can debug it further. So let's bring up that. In my VM, I use gedit. So gedit this message vop.log, and the other one I want to get up also pa report text.log. All right. So in my message.vop.log, I have only warning and I don't really have errors here. So let's go for another log file. ls. Let's check for the other log file. So if we don't have log file, we can actually make a log file from running. So let's see if we have a log file here. Okay, we don't have any vop log file, but let's see where is the error coming from. Is it from vop or is it from vsim? So we have two errors and we scroll up from our terminal. So one, okay, the error is in vsim. We can see the error is in simulation, but let's scroll up further to check on vop. Okay, seems like vop is running fine and there's no error from vop. So this vop.log message file is not helpful and we need the vsim.log file. And we check again from our make file. And then we see sim, we don't really have a log file here. So let's add a log file -l. Let's do it before the .do. -l vsim.log. And then we save. Let's try rerunning it again. Okay, we can see after the run is finished, we can see the error is still there. Now let's bring up the log file from vsim.log. Oops. Okay, gedit. We should have it at our run directory. It's here, vsim.log. Okay, usually how I navigate the log file is I go to the most bottom, and then I scroll upwards to see where is the error coming from. There's two errors, so there should be two errors written in the vsim. Okay, we can see on line 108, the first error is QPA UPF illegal state reached. So it's complaining about this, and let's see what further information can we get from here. So the time is 20 nanosecond and the supply set is PD2 primary. So this PD2 primary reach an illegal power state and then we get an error. So the next, it gives us the file and then also the line number as well. Let's open up this file. Line number 5. Line number 5, and we remember PD2 primary reach illegal state. So we gedit that file. So once we go into the file and then we see the line number PD2, so we go back to the vsim.log. So here we can see pd2.primary reach an illegal error. So let's search for PD2 from the UPF. So pd2.primary. So PD2 primary is a supply set. So we created this supply set and then let's see further down what do we have from this PD2. Okay, we can see also here where we have this add power state for PD2.primary. So there's a few state that we added: state on, state off, and also state illegal. So state on, it shows that we specifically say it's on when we have full on of 1.2 and the ground is go to 0 volt. For off state, we see that the off state, the power is off and the ground is also at 0 volt. However, there's also illegal state that we mentioned here. The illegal state is when power is not equals to 1.2 and the ground is full on. So we know this state table for PD2 primary dot supply set. Now we have to check why is it giving us this illegal state. Then we'll have to check what kind of supply on that we gave to this PD2 dot primary. So let's search for, again, let's search for the log file again. Error state is here. PD2 dot primary and this UPF line number 5. There should be one more error. Let's see where's the other error. Okay, so we know that the power state is wrong. So we'll have to go into the test bench and then check the supply on. Because at supply on stage, we are giving them the voltage value. So we gedit our source and the test bench. So at test bench, we can see supply on for VDD2. Because we know from the error message, the timestamp is 20 nanosecond. So if we see from the initial block and right after 20 nanosecond, the supply on given to VDD2 is 0.8. So anything outside from what we specify in the state table, anything outside of 1.2, we will get error. So to fix this, we can easily change the supply on to 1.2. So we can get this power domain on again at 1.2 and then we rerun it. So now we can see the error is actually gone. So the error is actually an easy fix. So anytime you see an error with power aware, you don't have to worry. You just have to remember where to find the log files and everything. So let me give you a reminder again. So if you have a PA generated report, then you will have to check from the reports, PA underscore reports. So inside PA underscore reports, the general file that you would like to see is report.pa.txt. And this file, actually, we haven't seen it yet. I haven't shown you, but it's easier to debug from the file itself. So if I do not want to reload this because I want to see the report that we're having just now. So vd2.primary. Let's check for vdd2. vd2.primary here. We can also see all of the supply set and also the isolation. Let's search for isolation as well. And then anything else that you like to see from the pa.report, you can just check from this report.txt. Yep. So that's basically how you handle this error message from the first lab. So if anyone have any troubles accessing the lab or bringing up the environment, let me know. Then we can check from your environment as well. So I've just shown you how to fix the error. Then maybe you can try fixing the error from your end and then see if it's makes sense to you. And if not, you can just directly ask questions. Then I can answer back here as well. All right, I'll give it like 5 minutes for you guys to get familiarized with this first lab, and then we'll move on to the next lab. So just to take note as well on this error line, we also have to see the line, 2 lines above, where it fires this violation of QPA UPF package function as similar to the report. So similarly at 20 nanosecond, it fires a supply on applied on this, but the voltage is 0.8. So this is actually causing the error, and it directly gives you the line number 53 on test bench. So line number 53, the one that we fix this line, then if we change this back to 1.2 as specified in the power state table, it will fix this error. All right. If and there's no issue on the first lab, then we can try on the second lab as well. So on the second lab, I've sent this PDF file. I'm sure you guys have the access as well. If you guys don't have this PDF file, let me know. So this PDF file is the lab that I sent to you on PA_lab_24. So if you want to go through all the labs, there's 6 labs in this zip file. And then this PDF will guide you through each lab individually, so one by one. So on the lab 1, we're seeing X in a simulation. So by going through this PDF file, we can see how to navigate ourselves through seeing an X in a simulation. So you guys probably can try this out as well. Let me bring out my own VM. So first thing we do is we have to always see what's in the makefile. So makefile in this case is similar as the run that we did earlier. So we have make all. If you want to bring up the visualizer, we also have make vis. So all is the same. Once you familiarize with yourself on the compile, optimize, and simulation, then you shouldn't have any issue with the all this flow phase with CrestaSim. So on compile, we just do a clean compile. We remove a work directory, and then we create a work directory, and we just vlog to compile all of the system verilog and verilog file. So we have -l here to generate the log file, and also to specify -sv as a system verilog compilation. Then after compilation, the optimization phase, we have vop test, which is our top instance. And there's also a suppress here for a suppressible error. And -pa underscore UPF version, here we specify which PA version that we are using. In this case, we are using 2.1. And then to load UPF in, we use PA underscore UPF, new.upf. And to specify PA top, we specify instance test and then T as our PA top. To generate PA checks and enable static check, we use PA underscore checks equals to S plus D. So static and dynamic together, it's being generated. And to generate the PA generate report, we use PA underscore gen report. And to output the log file, and we can also use, this is redundant, we don't really need this. And then we output the optimized DU unit and -debug plus design file. At sim stage, it's the same. We do vsim, and then console mode, your optimized DU name, -pa to enable power aware verification flow, -do, and then we have a run.do file. We might have to see what it is doing here as well. Then we have our wave file, which will have all the wave information logged in qwave.db. So for now, let's see what's going on in this do file. So this do file is actually just run all and quit.f. It's very straightforward, so we don't really have to worry about this do file. Now, let's see what the lab are saying. So first we cd into the directory. And then we take a look at the makefile to understand the options. And then now we run the test case. So we just do make all. Let's try making all. So I've done making all, and then there's errors reported, but you don't have to worry about this error, as this is intended in the lab as well, as similar as the previous one. So we just have to go through the lab guide, and then we'll just go through everything here, and we should be able to fix this error without a big problem. So we should also invoke the visualizer. For the time being, I have removed visualizer option from make all. So we invoke it ourselves here. So now we can see the visualizer for this lab has been invoked, and we can actually see a lot of information from this debugger. The first thing I always do is I open up the instance to check how many instances that we are dealing with, and then what power domain is it associated with. So from here itself, we can see there's a PD top, PDSW1, and PDSW2 for all of the hierarchy below S1. So let's see from the guide S again. So it asks us to do in a transcript window, do case one wave dot do. Let's do this. Select text, let's copy. Then let's bring up our transcript window. Oops. Do your case one wave dot do. So what this does is it just add a few signals that we are supposed to see to our wave window. So we have added a test under .t.data int, and then DAT clock reset. All of the signals should be added in here. So let's bring up this, maximize this wave. All right, then we can see in a better view. So without looking at the PDF file again, we can see, as mentioned in the session earlier, there's a red crosshatch, meaning there's a data corruption here. You can see a lot of things, signals are being corrupted. So test.t, so instance.t is being corrupted. And I can also see ISO enable. It's not enabled during this session, this time, but it's enabled here. Let's full zoom this wave. So reset is down and ISO enable is up. And then this another enable signal is also up, is low here. So just by looking at this, we can see that when there's no enable signal, then this test.out1 is X, it's corrupted. But if the enable signal is on, then it has a clamp value. Let's say, for example, if I'm not wrong, this isolation strategy is clamped to 0. So this test.t, the test.t.out1 is 0 here. And again, there's no ISO enable signal here, so that's why it's unknown here. And if it's enabled again, it's 0. Let's see what's wrong with the lab. So we should change the time to 2100 nanosecond. And we're supposed to see out1 is going to X. Let's change the timestamp to 21. Okay, out1 is going to X at this point. Okay. So here it is asking us to trace the driver of this signal, which is F1Q. And then we can use logic code in hierarchical mode. So let's do that as well. So this is the driver for it. Let's bring up logic code. Then we can add this signal to waveform, and then we can see the signal is going to X and shown in different red crosshatch, which indicates the X is due to corruption as shown below. Let's add this F1Q to waveform. So we can see a difference between the X from RTL and the X from PowerOS simulation. So this is due to corruption, as mentioned in the PDF. And we can further check why is it being corrupted and at which power domain it is being corrupted. So let's check that, minimize this again. So it's in F1, and then if we hover over, it will say that at this timestamp, the UPF sim state is going from normal to corrupt. So we can also check more details in Power Aware domain window. Then we can notice more different signals that are being corrupted. Let's bring up the Power Domain window by doing this, right-clicking on PDSW1 on F1. Okay. Then we can expand on this power domain, and then we see all of the signals here. So let's try adding this power domain to the waveform. Once the power domain is added to the waveform, we can expand the power domain and all of the signals down here. So this power domain view will be different because this is based on the sim state. And we can see that during corruption, we have the word corruption as well, corrupted. And that is because our primary power is being turned off. Here. So from this power domain window, we can also trace what made the supply to be off in the click on this cone. Let's try clicking on this cone as well. Then it will bring up another logic cone, and then let's say if we expand it, gives us a buff. We can expand the buff. Let's try to expand the buff as well. So then it says that in the waveform prior to going to PD off state, PD SW1 current state is undefined. So this is again because it's driving full on and 0.85 volt is defined in PDFW1, but full on is 1.0. So to fix this, we just have to make it switch on, and we can edit the file tb2.sv, and then we change the supply on call at line 38 for it to be 1.0 instead of 0.8. Okay, let's try doing that. Change this to 1.0 VDD1. And let's try running it again. Let's try doing the same thing. We add the wave. Can easily add it from here as well. Just add it from F1, add to wave.
Hi, Jason, can you hear me?
Yep, Jimmy.
Oh, yeah. I just double check if you're saying or your mic is off.
Oh, okay.
Okay.
Can you hear me? Am I audible
Yeah,
just
yeah,
now
yeah.
as well?
Yeah,
Oh,
yeah.
okay, okay.
That's okay. That's okay.
Yep. Yep. So that concludes on the lab one. So if anyone have any issue with lab two, let me know. If else, we can also try to proceed with the other labs as well. There's quite a lot of labs that we can do. If you want to go into more detail on each of the error message, you can also continue from the PDF file from the lab 2. Then you can check out all of the errors, and then you can see all of the PA errors coming from dynamic checks. And once you follow through the detailed PDF file, you can actually try to know how do we debug this PA error. And it may take some time, but it's good to go through this lab on case one because it's a very comprehensive lab. And if you guys have any low power verification debugging to do, you can, if you remember all of these steps, you should be fine once you encountered any error. So on my side, let me try to continue it here as well. So the next is to check the message viewer in Visualizer via the message generated by runtime cross-same dynamic checks. So let's open up the message viewer. And from here, we can do some filtering. Let's filter configure to show category column by clicking 3 columns. Let's see, icon, and then do category, filter all the messages except for PA category. Now by doing this, we can see all of the PA categories and we can debug low power verification easily. So we should also sort it, sort it by severity. Let's see, severity by error so that we can debug the error first. So only error. And then we can see at time 2100 nanosecond, there's a lot of violation being fired. So this violation being fired is indicating that the input to power domain PD top, PDSW1 and PDSW2 have toggled when this power domain is powered down. So depending on the design and implementation, this could be an issue. In this example, we are going to wave these checks using fine-grained control command for PA dynamic checks PA message. So in this case, we want to turn this off for a specific domain. And to do this, we'll need to bring up our .do file again and then uncomment the 3 lines. So let me show you how do we wave this message. Let's quit out from Visualizer first. And then we bring up our run.do. So these are the way you can wave the PA message. So write PA message and then dash disable dash check IDs, and then this is the message that we wanted it to wave, and for this power domain. So let's save this and then we run it again. So by using the steps mentioned previously, when we do it again and then we sort it by errors, then we can see the message generated by power where dynamic checks were enabled at VOP. So there's actually 3 types of issue being caught and can be observed at the message. Let's check from this as well. Let's do the filtering again. Click this one. We sort it. We get the category out. And then we are only interested in power aware messages. And then we prioritize error only. So we have the real error message here. Let's go back here. All right, so the first one seems like there's a missing level shifter. So this QPA, UPF missing LS check. This violation means that we have a missing level shifter. And the message moving forward from there is missing level shifter for the power domain, PDSW1. So the sync port, source port is from Q and the sync port is D1 on the power domain PDSW2. So this error fires each time the power states of either two of these power domain transitions. So this error occurs at 10,900 nanosecond. That is due to isolation not being enabled when power source domain PDSW1 is turned off. So this is impacting the signal of the source of the source signal from Q. And this indicates that the power down sequence was not correctly executed by the power logic control. So at this time, we see an error where at power up of PDSW1 indicating there is non-retentional resistor with asynchronous reset. So let's analyze the first error message. So we can open up sim check again. The sim check window. So let's see our PA sim check window. And then we're looking for missing level shifter. And we can click on the wave icon to add all of the relevant signals for this to debug. Let's try doing that as well. So now it added all of the signal. Let's maximize it. So all of the signals are relevant to this issue. So we can check it from here. And the timestamp they are giving us on the violation select error as well. So let's take a look at this wave, for example. So looking at the wave window, we can see PDSW1 primary 1. PDSW primary 1 is operating at 1 volt, while PDSW2 primary 2 is operating at, let's see, 1.2 volt. So 1.2 volt here, and then 1 volt at here. Then using the logic cone to trace the drivers of this D1 to see if there's any level shifter between the sync and source port Q, you'll notice that there's no level shifter strategy in this path. So let's try to trace the driver of D1. Logic cone view. So we notice here there's no level shifter strategy. So let's continue from the lab. So right now we have to open up our UPF file again. And then we go to line 71. We can see the UPF code for level shifter strategy. And this strategy is currently being commented out for the sake of the lab. So we will have to switch on this level shifter strategy and try to make all again. Right, let's check from the UPF file. So new.upf. And then we can easily search for level shifter. Okay. PDSW1, PDSW1. So on line 71, we have this level shifter here. So this is one of the strategy that we can use on level shifter. So to easily deconstruct this strategy, we set level shifter and then we name our level shifter PDLS and where the domain of the level shifter we wanted it to be. And where is the crossing? The source of the crossing is from PDSW1 and the sink is from PDSW2. And since that we are moving from 1 volt to 1.2 volt, we have to specify dash rule, so low to high, and then the location at parent. So we uncomment this and then we can rerun it again. Right, and then once we have it up again after rerunning, we go back to the message viewer. We'll do the same thing. We get the category on, and then we focus only on the power aware and the error message. So now we can see the previous level shifter violation flag has been removed. That means we successfully debugged that issues and the level shifter strategy now is in place. Let's check. Now let's check these other two errors. Let's continue from the lab as well. So on the remaining two error, and let's see, mentions that on line 58 of test bench TV2 is acting as a power control sequencer. So here we can see there's a task called power down normal. And let's scroll down further on that file and see the task definition for this task and see how the power down sequence has reset and isolation control enabled in the right order, similarly for power up sequence. So for this correct sequence, this error condition are not seen. So let's check from the test bench file on line 58. Then we can double click this instead of going to the file, and then it will bring us to this. So this is the UPF file. Let's go for the test bench file. And then we go to line 58. So this is the sorry. So this is the task definition for power down normal as it is being called here. And let's see. So at 15, we should enable it and then, okay. So this should be the correct sequence for the isolation. And if you want to change the sequence, we can change it. And once we have this correct sequence going on fine, then this error message should be waved already. That basically concludes how we deal with the errors that we see from the message viewer. And once you reach this place, the same as mine on your end, then that means we concluded on lab 1. On case 1, so there's a few more lab cases. I think there's total of 6 lab cases. You guys can take a look and explore how to advance on this debugging verification flow. So there's a few more minutes. Why don't we take 15-minute breaks first, and then we'll come back at 11:40. And if there's any question during 11:40 before lunch break, I'll happy to take on the questions. So let's come back at 11:40 for a short break.